This will be an introduction to infrared telescopes with a few facts about the James Webb Space Telescope. For starters, I'll just mention that the infrared part of the spectrum starts at about 700 nanometers and continues up to nearly 1 millimeter. As with most parts of the electromagnetic spectrum, the boundaries are not that clearly defined. The James Webb Space Telescope will study light with wavelengths from about 600 to 27,000 nanometers. Infrared astronomers tend to use micrometers, also known as microns, instead of nanometers. 1 micron is 1,000 nanometers, and so the James Webb Space Telescope will study light from about 0.6 to 27 microns. Why do we even want to study infrared light? One of the major reasons is that it's just part of the overall picture. If we want to understand everything, we need to consider all the parts of the spectrum. Sometimes the light given off by things is just not in the visible spectrum. When we look to the farthest reaches of the universe, we're looking way back in time because it takes so much time to reach us from there. And over time, that light has become what we call cosmologically redshifted, so that it isn't even in the visible spectrum anymore. If we want to study the very early universe, we have to study infrared light. Sometimes, though, things just don't emit much visible light, but they do emit a fair amount of infrared light, so that's helpful. For instance, look at this planet with rings. That's something, isn't it? Turns out Saturn is not the only planet with rings. In fact, all 4 of the Jovian planets, Jupiter, Saturn, Uranus, and Neptune, have rings, but it's only Saturn that has the visible rings. If we didn't use infrared light, we might not know much about those rings around Uranus or the bright spots on the surface of the planet there. By the way, the Hubble Space Telescope took this picture. It could just see a little ways into the infrared, and it was able to spot the bright spots and the rings that you see here. Here's another infrared picture of Uranus. The rings show up particularly well in this image, as do several of the moons. This picture was taken from the European Southern Observatory, which is in a high-altitude desert in Chile. We can do a little bit of infrared astronomy from a few dry, high-altitude spots. Light with longer wavelengths has the ability to penetrate some regions in space and elsewhere that shorter wavelength visible light does not get through. Here's a picture, not such an astronomical object, but on the right is a picture taken with an infrared camera, and that shows infrared light that is converted into part of the visible spectrum so we can see the images. Look how brightly the human glows. They're at about 98.6 degrees Fahrenheit or so. Also note how easily the infrared light penetrates the black plastic bag, so it can go right through some things. But it doesn't go through glass. Look at how the infrared light doesn't go through the person's glasses. They're completely blocking it. Here's an astronomical object, a cloud of gas and dust that's obscuring whatever is behind it in the visible part of the spectrum. But when we look in the infrared part of the spectrum, we can see that stuff. Look how easily the infrared light penetrates that cloud. We can see the stars behind the cloud that were completely blocked before. We can still see that the densest part of the cloud is blocking some of the infrared light, although we can also see stars through it that we couldn't see before. Here are some of the challenges to doing infrared astronomy. Water vapor in the air is a big absorber. The few places on Earth where we can do much infrared astronomy are very high and dry, such as the Mauna Kea Observatory in Hawaii. It's at nearly 14,000 feet elevation. A whole bunch of telescopes up there, by the way. It's almost as high as Mount Rainier. Another place where it can be done is the Atacama Desert in Chile. It's not quite as high altitude as Mauna Kea, but it's extremely dry there. And those places, there isn't much water vapor in the air above them. This chart shows how well the Earth's atmosphere transmits radiation at different wavelengths. The higher the purple reaches on the diagram here, the better the atmosphere is at letting in that radiation or letting it out. The axis on this is in microns, the horizontal axis, and the stretch from 0 to 1 microns includes the visible spectrum, which is from 0.4 to 0.7 microns. And you can see that in that region of the spectrum, the atmosphere transmits fairly well. You can see which molecules in the atmosphere are causing the absorption of infrared light at different points on here. It's mostly water, H2O, and carbon dioxide, CO2, but there's also some absorption caused by oxygen molecules, O2, and possibly some O3, which is a different oxygen molecule called ozone. It's a little hard to tell. The subscripts on the elements are a little bit blurry, but I think a couple of those are O3. A more technological challenge to infrared astronomy is that the usual detectors in digital cameras don't work very far into the infrared. The Hubble Space Telescope has detectors that can work from the near ultraviolet at about 100 nanometers into the near infrared at 1,000 nanometers, but no further than that. In the James Webb Space Telescope, they're using different kinds of detectors for different parts of the infrared spectrum. This next little bit's nothing you need to worry about, but for the near infrared, from about 600 to 5,000 nanometers, the detectors are made of a combination of mercury, cadmium, and telluride. And for the 5,000 to 28,000 nanometer mid-infrared, the detector is arsenic-doped silicon. The biggest challenge for infrared astronomy may be this. At ordinary temperatures, things glow with thermal radiation in the infrared part of the spectrum. Everything we're familiar with that surrounds the telescope glows. Some of it can be blocked. We've done that with visible light in cameras since cameras were first invented, but what do you do when the light detector itself is glowing? You have to cool the detector down. You can put it in the shade. This is essentially what we do with visible light cameras, where the only time the detector is exposed to light is when you click the button. But with infrared, we have to go much farther than that. When the light detector itself is glowing, you have to cool it down further. Things that work for that are liquid nitrogen for temperatures below about 77 Kelvin, but not too much farther below. For even colder temperatures, you can use liquid helium. That's down at about 4 Kelvin. Unfortunately, both liquid nitrogen and liquid helium will eventually run out. The first space infrared telescope used evaporating liquid helium as the coolant, and it ran out after only 10 months. A later space telescope, the Spitzer Space Telescope, also used liquid helium a bit more efficiently, and it worked for about 6 years before running out of liquid helium. It continued operating in the near-infrared part of the spectrum after that. Cryocooling is like a sort of refrigerator, so the process is more complicated, but it will work to get things to the lowest temperatures, and that's what they're having to do with the James Webb Space Telescope. So that brings us to the James Webb Space Telescope. After many years of development and many years of cost overruns, it was finally launched on Christmas Day of 2021. The cost was nearly $10 billion. It was sometimes referred to as the telescope that ate astronomy, because many of those dollars meant other research projects went unfunded. Many of those dollars weren't for the materials so much, but they were spent on the thousands of people and the thousands of hours they put into the project. The telescope is certainly the most complicated piece of equipment ever launched into space, and to guarantee that it would work once up there, everything had to be tested, and designed in a way to overcome every problem the designers could anticipate. They identified 344 different points in the deployment of the telescope where if those things failed, it would be an end to the mission. And they had to figure out for every one of those how to make sure that it didn't happen. To put things in perspective, $10 billion is almost as much as the National Football League will get every year for the TV contract it just signed. So it's a lot of money. Or not. The approximate unfolded mirror size is 6.5 meters in diameter. That's much larger than the size of the rocket part that it went into. And so they had to figure out a way to unfold the 18 hexagonal mirrors that make up the big 6.5 meter diameter mirror. In addition, there's a 5-layer sun shield that's as big as a tennis court that also had to be folded into the rocket and then unfolded in space without damaging it. So how does this telescope overcome the challenges that it has to? The glowing atmosphere, put it at the L2 point, a long ways outside the Earth's atmosphere. The glowing Earth and the Moon, same solution. It doesn't have a building, it's just a telescope with a giant sunshade. You may have heard about the L2 point. That's short for the second Lagrange point. And that's a point in space where the telescope will orbit the sun with the same period as the Earth. Usually, something that's 1 million miles farther from the sun will take longer to orbit the sun, and it would fall behind the Earth in its orbit over time, year by year, get farther and farther away. That's just Kepler's third law. But for an object at the L2 point, the combined gravity of the sun and the Earth work to make it keep up with the Earth in its orbit. The giant sunshade does a lot to cool the telescope most of the way to where it needs to be. It cools it down to under 50 Kelvin. A cryopump will cool those instruments that study the mid-infrared and have to be cooled down further, getting them down to about 6 Kelvin. That's just 6 Kelvin above absolute zero. And then the sensors, they built special detectors for the infrared. The cryopumps don't have coolant that's going to run out, so they should work as long as the moving parts move and the electronics of them still function. So it should last quite a while. Some fun facts about the Space Telescope. They made the mirrors out of beryllium. Actually, the mirror is gold. The beryllium is just the support for the thin layer of gold that's on top. And they use beryllium because it's strong for its weight and it stays stable for wide temperature ranges. Ordinary things, if you cooled them from room temperature or whatever the temperature was in French Guiana where they launched it, down to just a few degrees above absolute zero, they might deform. But they had to plan on those beryllium mirrors not doing that. They used gold for the plating because gold reflects 99% of infrared light, and things like aluminum and silver aren't as reflective. Gold is also highly unreactive. It's not going to tarnish like silver or aluminum might. For the entire telescope, they used 48 grams of gold. As a comparison to that, when I make a cup of coffee, not a cup of coffee, but a pot of coffee in the morning, I use 36 grams of coffee beans. That's about a golf ball sized piece of gold that they used on the thing. And at today's prices, that's about $3,000 worth of gold. And it's spread in a 100 nanometer thick layer all the way across those 18 hexagonal mirrors. It's planned to have a minimum 5-year lifetime. However, when they launched it, they were able to be efficient enough with getting it to the L2 point that the spacecraft now has enough fuel to stay there for 10 years. and it actually requires fuel to stay there. So, no servicing missions are planned. The Hubble Space Telescope was designed for updates to have servicing missions, but it's only a few hundred miles above the Earth's surface. They were able to send the space shuttle up for servicing missions. In fact, the last servicing mission was piloted by a former BBCC student who went through the flight program. The James Webb Space Telescope wasn't designed for servicing. It's 4 times farther from the Earth than the Moon, and we've never had humans beyond the Moon before. But who knows where space travel might take humans in 10 or 20 years. With SpaceX and other private companies putting people in space, they just might decide to sign a contract with NASA to service the James Webb Space Telescope. The James Webb Space Telescope slowly travels around the L2 point, and it's actually almost 300,000 miles away from it while it orbits that thing. It takes 168 days to orbit around there, and it does that while the L2 point, which depends on the Earth, is orbiting around the Sun. And it's kind of like the Moon orbiting the Earth while the Earth orbits the Sun. Staying close to that L2 point requires small corrections to the telescope's position fairly regularly, and it is that will consume the fuel of the spacecraft after about 10 years. That's a bit about infrared astronomy and the James Webb Space Telescope.